So this problem deals with alpha decay. Specifically in my case, I've got the alpha decay of actinium-226 into francium-222. And I'm asked to determine the disintegration energy, which is also known as the Q value, the kinetic energy of the daughter, the kinetic energy of the alpha particle, and the speed of the alpha particle. Okay, so there's a lot to unpack here. First off, what the heck is this? Disintegration energy Q value. So the Q value is just the total kinetic energy of the daughter nucleus and the alpha nucleus. So I could just write that as a simple equation. Q equals the kinetic energy of the daughter plus the kinetic energy of the alpha particle. Now this is what Q is, but at least for this first part, it doesn't help us because we don't know Q, we don't know the kinetic energy of the daughter or the kinetic energy of the alpha. In fact, we're asked to figure out all three of these things. So what we have to use instead is this other formula, the rest energy of the parent nucleus equals the rest energy of the daughter nucleus plus the rest energy of the alpha nucleus plus the Q value. Okay, what is this? Where did this formula come from? Well, this is actually just conservation of energy. Before the decay, all we have is the rest energy of the parent. Now, that's because, let me just clarify this, that's because we are doing this from the frame of the parent. And in the parent's frame, their velocity is zero, so they only have rest energy. Okay. So only rest energy in that frame, and after the decay, all the other energy must have come from this. So that's the rest energy of the daughter, the rest energy of the alpha particle, and whatever kinetic energy they each have. That all came from this. So this formula here, really straightforward to get Q now because you have the masses, they're stated up here in the problem. Notice that these masses are in terms of U, atomic mass units. I recommend that you convert these into mega electron volts per c squared. The conversion factor is up above. I can go ahead and write it here, but it's 1 atomic mass unit equals 931.5 mega electron volts per c squared. That makes your life a lot easier because you put that in and you're multiplying by c squared. So the c squareds cancel. So definitely I recommend doing that for this part, but I'm going to let you handle that on your own. It's the second part of this problem that is less obvious, is tricky. And that's figuring out the kinetic energy of the daughter. Because you go through this and you get Q, that's great, but you still have two unknowns in this formula. So how are we going to get the kinetic energy of the daughter? And the answer is we're going to use momentum. So we know from conservation of momentum in the parent's frame, first let me write down law of conservation of momentum. We know that the initial of my system has to equal the final momentum of the system. So initially in the parent frame, there's no momentum because the parent nucleus isn't moving. Afterwards, we have two objects. We have the daughter nucleus and we have the alpha particle. Their momentums have to add to zero. Now these are vectors. I'm adding two vectors together and get zero. That means the two vectors must be anti-parallel and they must be equal in magnitude. So that means the momentum, just the magnitude of the momentum of the daughter has to equal the momentum of the alpha particle. Okay, so why is this important? Well, it's not immediately obvious, but let me just keep working it. So I've got the mass of the daughter times the velocity of the daughter. And I should mention that I happen to know that we can treat this problem classically. That means we don't have to use relativity for it. So that simplifies our work. Now right here, good trick is to go ahead and square everything. It won't be obvious at first why I'm squaring everything, but I think you'll see it before I get to the punchline. Now what I'm going to do, and this may seem even more mysterious, I'm going to divide by the mass of the alpha, just one of them, not both, just one. Now, hopefully, maybe now I should say you're starting to see what I'm doing. You can see I only divided by one of these. I didn't divide by both. So one's over here, the other one's here. And I have m alpha v alpha squared. So if I just also multiply both sides by 1/2, this is the kinetic energy of the alpha particle. And on the other side, ignore this square for a sec. I've got md times vd squared over 2. So I've also got the kinetic energy of the daughter. But this was md squared, so I only needed one of these to go into the kinetic energy. So I have the other one, and I still have the m alpha. So here we go. I've got this relationship, which combined with this will allow me to figure out the kinetic energy of the daughter. And that's because, of course, I already figured out Q at this point. Q is already figured out. So these two in conjunction, two equations, two unknowns, I can figure out the kinetic energy of the daughter. Once you know that, pretty straightforward to get the kinetic energy of the alpha particle. Notice down here, you're also expressing it as essentially a factor of the total kinetic energy between the daughter and the alpha particle. And the reason why you're asked to do this is so that you can see that even though the alpha particle is way smaller, it has the vast majority of the kinetic energy of the system. And so as a result, it gets moving pretty fast. Speeds of up to 5% of the speed of light are quite common. And this is why radioactivity is dangerous to us, because these alpha particles come out incredibly fast. They have a lot of energy. And if they strike a molecule in our body, for example, the DNA, if they do that, they can cause it to mutate. They can do real damage. And that's the danger, because that can cause, if the DNA gets damaged, that can cause the cell to die or to mutate. It could turn into cancer. That's bad news. So that's what we're trying to see here, is that these alpha particles that come off in this alpha decay, these alpha particles are basically tiny bullets, very tiny bullets, but they can still do a lot of damage.